So our next speaker is Ian Houson, also from Strathclyde, and he's going to tell us about digital first approach to design and delivery of mefenamic acid particle attributes.
So I'm going to talk to you today. I'm summarising quite a lot of work from a lot of people, both at Strathclyde and then also at Loughborough. So the work has been published earlier this year, and so a lot of the detail is in there. So this is actually a bit like a prequel talk. So you've seen the quality by digital design, you've seen elements of MicroFactory, and I'm going to talk about the bit beforehand. So hopefully it's a little bit better than the 2 or 3 Star Wars prequels that came out after. But anyway, that's just my hope. So I'm going to cover a number of things, so we'll get on. So context of the work, and I think Ivan covered this really quite well yesterday. Why do we care? So faster, cheaper, better medicines, less material, more sustainable. I'm sure there's a few other drivers that I've forgotten, but fundamentally that's really what we're here to try and do. And we've seen a lot of development of digital tools. They've been brought out, but they're quite often used in isolation. We use a bit here, a bit there. But how much can we actually go from start to end in a design of a medicine? So admittedly, in CMAC, we probably can't do the whole end-to-end yet, and this work started, it was conceived probably, we're nearly at the end of 7 years, so 7, 8 years ago when the proposal was written. So this is really about saying how much can we actually genuinely design and develop. So the work I'm going to talk about is focused on crystallisation and then the isolation, so filtration, washing and drying, and there is an element of performance as well, although I'm talking more about API dissolution performance rather than drug product performance. So the compound that we picked as a starter was mefenamic acid. I guess we work in an academic environment, so there's a couple of things that we always go for. Let's hope it's not too toxic, and it needs to be relatively affordable. But also, particularly for us, we were interested in a compound where we knew particle size was going to be important for the dissolution of that material. So I think that the design, develop, test and compare is fairly standard and applies across a whole range of things and been talked about much more eloquently than I'll cover here today. So what we wanted to do was challenge ourselves a bit. So we wanted to pick 2 particle sizes that we were fairly sure would deliver different dissolution performance, have different product attributes. So we wanted to have one that would be driven by the pharmacopoeia requirements and then one that was different. At this stage, we didn't know what different was, but we just know we wanted to challenge ourselves and what the models were and what we could do. So how do we decide what we actually needed to make? So we started off with, I think probably where most people start, the BCS classification system, and then there's a slight variation of that, an update of that on the BASF Zoom Lab, which you can do online. Obviously, without having a commercial compound, it makes it quite a lot easier to use that tool. You're confident to put it in. But what was interesting was actually the 2 systems were giving us slightly different particle size targets in order to achieve the dissolution at the required dosage, so 250 milligram dose. And we're looking at a D90 of less than 60 micron or a D90 of less than 42 micron. So 2 models, 2 slightly different approaches give you 2 different answers. Maybe not unsurprising, but we thought, well, which one do we want to pick? So we went a little bit further, and so using the GCOAS model that's built in GPROMs, we did some more modelling there, really looking at particle size and then the dose percentage of release per unit time. So based on that, we sort of went, well, actually the smallest size, the D42, looks a good one. And also then, how do we pick something different? So this is slightly arbitrary at this point, but D90 of less than 120 micron was where we went. So those were our 2 target PSDs that we were able to design virtually. So at this point, we still haven't got any compound out, but we're starting to actually be able to design the particle attributes that we need to make. So the next bit that we wanted to do was go, okay, so that's good. So what are we going to do it in? So we don't have at this stage, we don't have that holistic synthesis workup crystallization piece built in yet. Claire talked really eloquently about that this morning, and that's something that we're looking to build to in the future. So really we've sort of got a nice place. We can start wherever we want to. So where do we want to start? So this as with a lot of this, one slide summarizes a lot of work that was done in the background in development. But actually, again, there's a lot that we can do digitally that means we don't actually get any material out. We haven't actually done any experiments yet. So a first screen is around using the GSK and the ACS as well, the green solvent guides around toxicity, the Montreal Protocol and things like that. So fairly quickly we get down to a short list of 33 compounds. I should say as well, sorry, one of the assumptions that we built in at the start was, if possible, this is a cooling crystallization. What's the simplest thing that we can possibly do that will make the development easier, the process run easier? So what we're initially targeting is, can we do a cooling crystallization? If we can't, we'll look at other options, but that's where we're starting. So we're able to do some initial Cosmo modeling. So this is really looking at boiling point down to the cooling point, and then some realistically, what might the yields be? What's my product mass intensity? How much yield would I get out in a reasonable cooling profile? So sort of, 10 degrees below the boiling point, down to sort of room temperature, 5-10 degrees. Things that we can do relatively easy in a lab. Industrial environment, you can go lower, but you've got the larger scale capability, and it's all a bit easier, but we did restrict ourselves in that. So we did some optimization of that Cosmo modeling by gaining some literature data. And so from that, we were able to pick 8 compounds. We did have a slightly larger number, but after sort of a bit of review of some of the chemical compatibility, we cut that down to 8 compounds. And we were able to validate that in the lab, and Chantal showed some of that, the evolution of that work that was done. So here's our screen, here's the results. We're starting now to build in some of the sort of more sustainability metrics, volumetric productivity, to really help guide us. And I think this was probably our first foray into broadening the questions we're asking the models. What's the additional data we should be doing that will help us make our decisions to get an optimal process throughout? So the other thing we did is, so with it being in the crystalline, we're able to take images. And I think probably for me as a background as a scale-up chemist, the bit I care about is what am I looking at and what am I going to worry about. So in here we've got things like the fairly qualitative descriptions at this stage, because the work was done a reasonable while ago. Slow agglomeration, fine needles, lots of agglomeration. Things that as a process chemist you start to go, uh-oh, I'm nervous about this. So it starts to highlight risks and enables you to build some risk assessment into your process, or at least say, okay, if I'm going to take this compound forward, or this process, this solvent forward, what's the additional things I need to be working out? Because inherently we're trying to do less experiments. So that means you've got less time to look at your compound and work out how to process it. What are the things that you worry about? So we picked 2-butanol as the main compound. It didn't have any of those issues at that stage. And from that, we were able to do some very rough work. So from the crystalline, we were able to get some rough kinetics. And fairly quickly, we're able to see, well, unseeded crystallization, that doesn't deliver the particle sizes we needed. But actually, if we do a seeded crystallization, we can hit the 120 micron target size, but we can't hit the the 42 micron particle size. And so from that, we're able to start now estimating what the processes are going to be. So for the smaller size, we'll go down a wet milling approach, and then the crystallization, we're going to do a seeded cooling continuous crystallization. It's where we want to go. So with that in mind, so at this stage, we've done quite a lot of development. We've sort of done some of our attribute control. Sorry, I did forget to say the other quality attributes we're picking are essentially the pharmacopoeia standards. So how do we deliver against those? So we've got some size, particle sizing. We've got a solvent system. We've got some guess at the risks and some of the concerns that we've got. So we went into the small particle process make, so this is the wet milling. So the nice thing about wet milling is it's actually pretty well documented in the literature. The models are all fairly strong here. And so we were found that really quite quickly, we were able to get some breakage kinetics. That fitted fairly well in the GPROMS model. And we were able to broaden that out then to expand the design space, both looking at things like the mill speed, the rotor configuration in the lab experiment. So this work really didn't actually take very long, so maybe a week or two of work at most to do it. And so from that, we're able to get some different mill configurations and attainable sizes. And actually what we're looking for, the D42 micron, we could actually have made with any of the rotors. There's spaces where you can get there. So in the end, we picked the coarse rotor for two reasons. One was around risk. We were seeing less foaming with the coarse rotor, and also it takes less energy to run it. It just uses slightly less energy inherently. So that was the system we went for. So the good news is that models work really well for wet milling. It predicts it really quite well. I think is within the zones in which we looked at it, certainly what we've found is that the lower RPM, maybe the model wasn't that good at predicting it, and so we're actually wondering whether there is a sort of a cut-off point at which the model starts to fail and it needs some additional work doing in it. But we're really quite pleased with this. We went, hey, this is easy, right? So so this one went very well. We made some nice material, and the bonus of this is actually once we were doing some more of the other work in parallel on the crystallization, that actually this would be really nice seed as well. So that's where we're going. So moving on, so this is work that was done by at Loughborough by Wei Li. So there is a lot on this slide, but that's because there was a lot of work done. So small-scale parameter estimation experiments, and then some uncertainty analysis, and then really some larger-scale one-stage and two-stage verification. So I think parameter estimation is reasonably well covered, so I'm not going to talk very much about that. The two bits that we were interested in are the uncertainty analysis, and I'll talk about that on the next slide, but also about the one- and two-stage MSMPR verification. So if you think now that the parameter estimations, they're all done on small scale, so they're all pretty small-scale materials. There's no slurry transfer. We don't have many PAT probes. You're running generally at fairly low supersaturations. You're not trying to drive the system too hard. Whereas when you go from that straight to a one-stage or a two-stage MSMPR, you've got quite a lot more practical considerations of how things go wrong. I think in hindsight, you actually maybe don't need the one stage. You can do it all in a two-stage MSMPR because certainly in our hands, a lot of the issue is we've been having is with slurry transfer, and certainly that's an area that we've done considerable development on, and certainly Lilly have published and others about how to do that with the vacuum transfer and moving forwards. So certainly that for us is a key stage, and I think there's still some smaller scale screening experiments we need to do around risk. So things about agglomeration, aggregation, are there some better small scale experiments to do to assess encrustation as well on the system. So in terms then of the model, so we were able to build a model quite well, and it's useful then to look at how that confidence intervals feeds through. So in this case here, it's actually pretty good at the growth kinetics, but the secondary kinetics, actually we've got a reasonable area of uncertainty there growing. So this has got to include, and Amal's talked really nice about this in her flash presentation, sampling, analytical, and remember it's compound error. It's not additive error. So once you build a number of those things into a model, you don't get a single number out of a model, you get a range. And I think we sort of tend to get a bit fixated sometimes on, it's this. It's not, it's somewhere in here. And that was some sort of real learning for us out of the process. So in parallel as well, Sarah Ottoboni and Chris Price were doing work in their team looking at isolation models. So this is not an agitated filter dryer. These are just the small-scale carousel. So it's all settling and then driven by nitrogen for drying. So a number of models they used there, quite a lot of custom modeling, which they've now published as well. A lot of the small-scale work was done in a biotage system, so we really like this. We've used it a lot and highly recommend it for the initial evaluation. We did do a test run, so linking on to the two-stage run that we were doing for the verification of the modeling. We kept that material and then used it to do a continuous run. We did do some model verification and revision, and then ended up with a full same system. Okay, so we've now made, I've sort of skated over a chunk of stuff here to cut straight to the results. That's all covered pretty detailed in the paper, which is why. So I think there's a couple of things here that we'd like to show. So the yield actually was pretty good. That was quite a good mimic on the thing. But what we found, and this is as we went from a 2-stage to a 5-stage, is actually we're starting to see greater differences between analytical methods, and also starting to see greater amounts of agglomeration in the process. So this is, you can really see it here. So if you look at the D90 in the actual isolated material, so this is measurement with a morphology G3, and then if you run that at different pressures, basically low pressure gives you, it is what you get, but the higher pressure tends to break up agglomerates as well. So if you run different pressure analysis and it goes down over time as you increase the pressure, that's really indicative of agglomeration. I guess the bit that we could sort of pat ourselves on the back is actually the primary particle size is pretty close to what we targeted, and actually within experimental and measurement error the numbers did fit. And when we come to look at some of the imaging techniques, you can see agglomerates, but I think one of the things that's been really interesting about this work is when you look at imaging, and this is particularly, I think, sort of you look at some pictures and you go, is that agglomerated or not? And you go, well, it looks sort of a bit like it's agglomerated, doesn't it? But how agglomerated is it? Is it just a sort of loose aggregate, or is it a proper agglomerate and I need to take a hammer to it to break it? So I think there's some more work we need to be doing in there as well as a research topic. But I think in generally in there we were pretty happy with what we actually managed to do. There was a lot of learning on the way. There was a lot of having to go back to revise the model a little bit. Wei talked a bit about the constraints in the model that you put in and how you have to go backwards and forwards as you find more things. And certainly a very recent project we've done on ibuprofen, we've had to do a lot more of that. That's maybe a discussion for another day though. So we went back and revised the model to include the agglomeration kernel. So we did some kinetics around that. And when you use the improved model, we were able to get really quite a good fit for the morphology results. It's maybe not such a good fit for the master sizer results. And I think that's one of the learnings as well is sorry, I meant to make this point and I forgot. So the numbers in brackets with the little star are master sizer results. So, okay, there is a slight difference in that one is a slurry, one is a dry powder dispersion, so we've had to filter, wash it and dry it. But fundamentally, the numbers are different, right? And in theory, they're the same product. So I think there is an element of you have to be careful, pick a method, stick with it. But we're seeing nearly 50% difference in some of these measurements. And if you're doing that for a seed, that's a 50% difference in your input surface area. Sorry, that's not 50% because it's not linear. I can't do the maths in my head quick enough stood here. But anyway, it's really quite a different product. So it is just, again, more learning, something to be conscious of when you're making it. And yes, I've got a number, but is it the absolute number that I really need, or is it just a number that's useful? Right, I need to probably get going. Okay, so so now the product performance testing. So coming back to that, so a little bit of the extra modelling that we've done using the G-CoAs is that actually the pH is, unsurprisingly, given that mefenamic acid has an amine group and a carboxylic acid, pH is quite important for this compound for the dissolution. So being able to model that, both sort of the D90 of less than 42 micron is the solid lines here, and then the D90 less than 120 micron are the dotted lines. So we do see there's quite a big difference, and the pH 7 is where we want to be. So where we set out then to do some work. So in this case, we didn't take the pharmacopoeia approach. So what we're trying to do here is mimic some more of the sort of in vivo performance. So by using biorelevant dissolution media, and that actually is what fits better with the models as well. Certainly G-CoAs assumes that as its dissolution media. So we had to develop and assess the analytical techniques that we'd got, and then obviously do the acid test on how good are we in all of our modelling. So we've done that. So Elke and did quite a lot of work on selecting the buffer system, and chose fasted simulated intestinal fluid, or FASIF is a much easier one, which is pH buffer of about 6.5, so 2 pKa units away from mefenamic acid, so should be pretty good. We also chose not to add the equivalent of the bile salt mimics. There wasn't really any significant interaction with mefenamic acid from the work that we did, so we went with the blank FASIF, and it's quite a lot cheaper. But that wasn't the main reason. And then Elke also had developed the analytical method as well for the dissolution testing. This box covers rather a lot of work, and it's a bit unfair to just bury it in one box. But there's actually quite a lot of work. Because we're just looking at the API portion, we're not taking a drug product. So we have to do some sort of, I could just drop it in and does it dissolve? Great. But actually this one doesn't. This one doesn't dissolve very well. It doesn't wet very well. Elke had all sorts of joyous photos of clumps floating around the top after the capsule had dissolved. So we ended up having to develop a tablet formulation to be able to actually get some decent dissolution performance. So again, it's one of those things, you've got a model that says how it dissolves, but it's actually how you deliver the material to the model that there's another question there. So we didn't fully get round to doing that side of it as well in this work. So here's the results then. So the orange dots are the actual results against the predicted line. So that's pretty good. I'll talk about the blue ones in a minute. So the orange one was pretty good, and that's actually interesting because if you remember, the orange one, that's actually agglomerated material when you measure it on the morphology G3. But what we've done is we've tableted it. And so we may be over-analysing the results, but actually by tableting the material, are we actually breaking our agglomerates back to the original particles? So if you remember the 128 micron, I think it was, we thought the basic particles were. So it's actually a reasonably good fit with the model. The material of 42 micron or less, so it's slower than predicted, and I think it's fair to say we don't know why. So I think that's where we are. We have some hypotheses, and if there's questions, Elke sat there. She'd like to say no, she's not. So yeah, so we're not really certain about this. Again, we do have some questions potentially about whether we're sizing the particle right. A dissolution model assumes a perfect sphere. These compounds, the mefenamic acid isn't too bad, but it's certainly not a perfect sphere. Yeah, we're not quite sure why that is. But other than that, it's not a million miles off, I think that's the thing to say. So yeah, 30 seconds. Okay, so in summary then, so actually for the first go at really trying to do everything, there's a lot of learning there. We used a lot of different models. We did have to get a lot of different skills. Chris, you were asking about the amount of materials. So this is actually developing 2 continuous processes with 1.43 kilos. So, compared to batch processes, you probably sat there looking, that's masses. How have you used that much material? But actually for 2 continuous processes, we're really quite proud of that. We think that's been a great work. And then we've done a lot of work sort of setting the way for the quality by digital design workflow. So Cameron's talked on that. Murray had a showcase, and there's a number of posters, 1 to 8, that will cover that. A couple of pieces of learning. I will be 20 seconds more, Chris. COVID was good. Hey, things you never thought you'd hear anybody ever say. But actually working from home sort of did actually give us that opportunity to get people upskilled, to spend some time learning modelling, start to predict things ahead of time. So when we came back, actually, that culture change was a lot easier than we thought. So what else have we got? We do need experimentalists still. We need a lot of them. That scale-up piece is actually harder now. If we're doing much more small-scale experimentation, then spending the time to minimize all the other phenomena that happen that aren't covered in the models is a key piece of work, and I think there's more work we need to do in optimizing that. So there's a whole bunch of other associated mefenamic acid projects that have gone on. I won't cover them there, but they're just covered. So these are sort of, I think, demonstrate the real value of having a key compound, sort of a grand challenge almost. I think that's what they were called in the bid, actually. So I do remember something, Alistair. So there's a whole load of spin-off work that gets done that people get excited at when there's a big challenge in there. And so Maggie's poster 33 talks about how we selected all the PAT and the flexibility of where you put your probes. So this certainly wouldn't be possible without a lot of people who've done a lot of work, and particularly I'd like to thank all the people on the left and Wei Li, who have done the majority of the work. The others are sort of academics. Helen has done nearly all of the organisation, so thanks, Helen, for that, and the collaborators, and thank you for your time.
Thank you, Ian. You've summarised a massive amount of work there. So I think we've got time for just maybe one question. We're a little bit behind schedule.
Hi, Ian. Thanks for the nice talk. Have you considered for the dissolution actually measuring specific surface area and then fitting a particle size to your dissolution and converting that to specific surface area and then comparing the two? That might take some of that measurement out of the equation, because obviously particle size, like you said, you're seeing spheres, that's not what you've got in reality.
So I think in principle, yes, it's certainly something that we talked about. I think the other question that maybe we have talked about is maybe actually doing some wettability experiments as well to evaluate the likelihood of how much of a problem it's going to be, and to help us design that.
You saw wettability issues with your suspension, so then when you go down in particle size, you still see it in tablets. That's kind of quite well known.
Yeah. So
I've got lots of thoughts. I'll come see.